Hi everyone, this is Zaid Rawi from BP. Welcome to this IchemE Process Management and Control Special Interest Group webinar. This one is sponsored by IPCOS. This webinar is going to be about PID loops, optimization of interacting PID loops. PID loops are a fundamental automation layer of almost all types of industrial production facilities. These PID loops need to be well tuned so that they can operate optimally, especially in scenarios where several of the loops interact with each other. Optimizing the tuning of multiple interacting PID loops will be discussed in this webinar, with case studies and examples presented to demonstrate the benefits of a systematic approach to tuning these PID loops. And we have Sam Dhaliwal, Managing Director of IPCOS, to present this. Sam is a practitioner of advanced process control for over 22 years, and he graduated from the University of Alberta in Canada with an MSc in process control, which was very much an emerging area at the time. Sam has also worked for Aspen Tech and co-founded Aptitude Limited, and now works for IPCOS in Cambridge. Please feel free to type your questions into the Q&A pane as we go, and we will do the questions at the end of the webinar. And I will now hand over to you, Sam.
Good morning. Thank you very much for joining this webinar. I really want to spread the message about PID tuning, hence the rather catchy title of Tune Your PID Loops, Please. So we'll start off with a brief introduction of IPCOS, probably just 2-3 slides, and then we'll get into the big part of the presentation, really talk about why is it important to tune PID loops, and then we'll get into a little bit more detail on interacting PID loops, how to identify them, what to look out for. And then we will go through a few case studies with some of our customers who have, for whom we have done some work and they have reported back benefits, and then some tips and tricks and methodology, and then we'll get to a Q&A session at the end. IPCOS has two business units, the Digital Oil Field and the Process Operations Excellence business unit. We are in the digital oil fields, we're really working with large multinational companies such as Total, Shell, Exxon, really looking at their oil field assets and looking at integrating the information that comes out of that and presenting it to all the different stakeholders. Process Operations Excellence, we are working largely in the field of advanced process control, and also more and more in PID tuning, as well as alarm management, benefit studies and that kind of area. So it's a service and software offering that we have, and really the objective is to improve the operation of your plant and to optimize it using different technologies. And you can see there some of our customers, again, global companies with a wide range of different industry segments. In terms of our offices, we have our headquarters in Leuven in Belgium, and we have also offices in the Netherlands, in Cambridge, which is where I'm based in the UK, and we have partners around the world, and also a small office in the United Arab Emirates, a slightly larger office in India, and also a small office in Houston. So really a large reach with several locations and obviously customers spread across the globe. Our core market is gas processing, refining, petrochemicals, chemicals, and really an emerging area now is power, waste, and utilities. That's a big part. And fertilizers and ammonia is where a lot of our APC technology is being implemented. So really, again, a wide segment of industries that we serve. In terms of our partners, in specific markets, we have partners such as Stami Carbon, In glass, we have Celsian. In cement, we have ES Processing, and we have some generic partners such as Siemens, AspenTech, and we really work with them on a case-by-case basis. We have also partners in the Middle East, such as BPC and Golden Falcon. They are, you could call them agents or partners in the Middle East, serving different countries. And we're very pleased that we are, having been, a reasonably small company, we have a global reach. In terms of our products, we're looking at 2 PID tuning products or softwares that we have developed ourselves and we license. They're called Inca Aptitune and Inca PID Tuner. Inca Aptitune is a multivariable PID tuning tool, and Inca PID Tuner is a tool that is used for tuning single PID loops. Then we have Inca MPC, which is our multivariable process control software, predictive controller. And we have Inca Sensor, which is the software that is used to develop inferential qualities. So if there is a product quality that you would like to measure, but there is no analyzer available to do that, then you would use a software such as Inca Sensor to build a model which can then be used to do the prediction of that particular quality. Okay. We are going to start off with the big part of the presentation, but before we do that, I would like to have a little poll question really about what tuning methods do you use at present. So if we just open the poll now, you will see something pop up, and we'll give you about 30-45 seconds to just respond. So you've got a few options there. There's the standard settings, there's a trial and error method, a heuristic method, and there's the rule-based method, and then there's the dedicated software. This is really to get a feeling for how people are doing tuning at present, and that would sort of give us an idea of at least this audience in terms of what we use. So I think we have about 70% of the people who voted so far, and we'll give it another 10 seconds and then we will close the poll. Okay, I think people are still voting. 76% have voted so far. Okay, I think we'll close the poll in about 5 seconds. So we've got 76% people who voted, 34% use a standard setting, 47% use trial and error, 42% use heuristic tuning-based methods, and then 33 sort of rule-based and 19% software-based methods. So, which leads me nicely to my first slide. And this is really, why do we want to do tuning? And I think some of us are, quite, would have experienced, for example, commissioning of a new plant. And during that process, you can imagine it's quite a hectic period where there's several activities going on. There's construction works, there's, laying of cables, etc. And the last thing on people's minds is actually to tune PID loops and to get the plant up and running. However, this often missed, activity is probably extremely important and would help you set your plant up and to stabilize it and commission it much faster. So what we found in our experience in working on several of these different plants is that 70% of the PID tuning parameters are default values that were put in when the plant was commissioned. So really that's not good enough. We know that even doing simple PID tuning can save you energy, whether it's on your gas-fired heater or your heat exchanger, and really as much as 10%. So yes, you should do that. These are opportunities that, these are little projects that you can do very easily, and you can really reap the benefit. Poor set point control, fairly obvious. If the loops are not tuned well, then it affects plant stability, not of just that particular plant, but also downstream plants. And then if the loops are in manual, there's an operability issue, because if you have disturbances or you have day and night swings, there's a rain shower that happens outside suddenly, well, you're not going to be able to control that part of the process where these loops are in manual, and that can cause problems or incidents. And a big one close to my heart is really about failed advanced process control projects. If the base layer is not tuned properly, then you could have situations where the APC projects are perhaps not as successful as they could be. So what are the symptoms of poor PID tuning? So poor operability, you have high levels of operator intervention. So the operator is constantly having to change set points, or he's sitting at the edge of his seat when there is a change in weather outside, or when there's a change in feed rate or type of feed. That's a symptom of one of the symptoms that, or one of the causes could be poor PID tuning. Excessive alarming is another one, where you might find there's a lot of process variables are straddling the alarm area quite often, and you're operating or pushing against the operating envelope constantly. And that's also not a good thing, possibly because you have oscillating variables that are kind of going in and out of alarm all the time. Product giveaway production capability is reduced. This is kind of directly related to profitability of your assets. So really, you don't want to be doing that. And obviously the underperformance of an advanced process control system that you might have. When should you be tuning PID loops? Well, we touched on this in the first slide. Once you've commissioned a plant, that's a good time to do it. Typically, DCS vendors will come out and do that for you. But like I said, most of the time, they are rushed to hand over the plant to you as the operating, as the company operating the plant, and they might not do a thorough job. So you might be left as the sort of engineer on the plant to deal with some of those issues. So it is a good opportunity to do this in a systematic way and recognize this right at the beginning and try and deal with it. After a major turnaround, obviously, if you've got new equipment that's come in, or you've retrayed columns, all these things will affect your how your base layer performs. So it's always a good time to check things out. If you've had a new DCS, or you've had new instrumentation put in, like new valves, or even a changeover of DCS from one type to another, you can imagine the algorithms are different, and you would want to transpose the DCS, the tuning in the DCS from one type of algorithm to another. It could even be that you're changing DCSs, let's say, for example, from Honeywell to a Foxborough system or Yokogawa system. Then those tuning parameters are different, so there's a lot of work to be done there to transpose those variables, and it's got to be done properly. So, and then debottlenecking is another one where you might come across opportunities to tune loops. APC projects are typically a good opportunity as well, specifically for that particular process unit where you are going to be implementing your APC. So again, you will spend time, making sure the base layer is tuned correctly before you move on to building the advanced process control system on top of that. So interacting PID loops, what are they? How do we, look out for them? So I've got a few examples here which might give you an idea about how, and hopefully some of these will be recognizable to some of you, and will give you an idea how to sort of identify these interacting PID loops. So you might have a heater with multiple passes. Let's say it's a heater with 4 passes, and then they join up, and then there's a temperature controller at the end, which is cascading onto a fuel gas flow, if it's a fuel gas fired heater. In that kind of situation, you've got all the passes which interact with each other, and the pass flows also will interact with the temperature at the outlet. And you will not be able to tune that optimally. So the operative word is optimally. So you can tune it, obviously, but it will not be optimal tuning. If you tune that problem as separate PID loops. So if you tune each pass separately and the temperature, outlet temperature controller separately, you will get some tuning that works, but it will not be optimal for all the different scenarios. Then you can have another example where you have a network of, say, hydrogen gas, or you have fuel gas network, a steam network, and all these networks, you'll have multiple consumers, so you have multiple flows going out, and you might have multiple flows coming in, and you can imagine there's a lot of dynamics in that kind of system. This kind of system also really is hard to tune sometimes because of sudden changes and the interaction between the different flows, and this is also an opportunity to use some interacting or multivariable PID tuning software to do tuning. Distillation columns, overhead temperatures and pressures, these are fairly standard in lots of different operating facilities. The temperature at the top might be cascaded onto a reflux. The pressure controller is, say, on a valve going to a fuel gas system or something. These things will also interact with each other. You couldn't just tune a temperature controller by itself and then tune the pressure controller by itself. You really have to tune them together as one problem, so you end up with the best possible tuning. Gas feed and expander pressure, this is a very specific example in gas processing, where you have a gas feed at the front end and you have an expander pressure at the back end of the process. One would expect, or I guess logically, that these things don't interact, but in fact they do. And again, it's a good example of where you would use multivariable tuning, because these two loops interact with each other. So the message here is really these sorts of loops or these sorts of problems, and these are just a few examples, really require a different approach in order for you to get optimal tuning. So let's get into some case studies. This is a gas plant in Saudi Arabia. This is a hot oil heater outlet temperature. So there are 2 heaters on this facility, and they provided hot oil that was circulating through the plant and providing heat duty to several of the distillation columns. And you can see here the blue is the temperature process variable, and the green is the set point. And he's swinging around, you can see the scale here is 315 and you've got 325 here. So that's about 10 degree swing, but typically you're looking at anywhere between 5 and 8 degrees swing in the temperature. And this is clearly not good in terms of the service of those consumers, because they're then being affected and perhaps product qualities are being affected. And what we did was we looked at this whole problem, and we tuned it using our technology, and you can see the before and after trend. There is still a little bit of a cycle. We'll be talking about, a degree or half a degree perhaps, or a degree at most in some cases. And really here, the customer, by just doing the single, fixing the single problem, there's significant benefits that they reported, which is greater than $150,000 per annum. And really those benefits are coming from the process units being able to control their qualities much tighter and pushing them towards their real limits. The second example I have is on the same plant, and this is a propane compressor. If you can imagine on a gas plant, really what happens is you want to chill, quite simply put, all the molecules coming in as much as possible and recover all the liquids, and then send the gases to a fuel gas system or a network, which is then consumed by power plants, etc. And what you have here is the suction pressure of this propane compressor, which is really the indication of the chilling capacity available, was in manual, which means that suction pressure, which is in green, is moving around all the time, and the control variable in this case is the speed of the compressor was fixed. And obviously if the suction pressure is moving, then really the temperatures are moving around in this gas train, which means that you have very poor control of the chilling and the quality subsequently. So here we put it back in automatic, and this is a plant, going back to my very first slide, that was commissioned recently, and really they never were able to put this compressor in automatic, because every time they did that, the whole system became unstable. So the operators just said, okay, we'll just keep it in manual. And you can see immediately, once we were able to tune it correctly, we were able to get this on control very well, and subsequently all the other variables associated with this became much better in terms of their controllability. We have an NGL recovery plant. This is another gas plant. This is a feed and expander type of arrangement where you have the gas feed coming in at the front of the plant and then goes through, so chilling and heat exchange. And at the back end you have a pressure, an expander pressure, and these two interact with each other, as will be clear from this model. What you see here is that if you increase the flow valve output, then its own flow increases, and also the pressure in the expander increases. And if you increase the pressure valve output, then also the feed flow increases, the PV, and the pressure reduces the expander pressure. So the way this model is generated is, you would imagine that these two valves, the flow valve and this expander, are in manual at the same time, and we make little step changes in each of them and observe the response, okay, which is what we see here. So this is an interactive 2x2 system. So if you were to tune these loops separately, you would never get them right. So we ran this through our software and we got some tuning results. This was an ABB DCS. The blue is the previous tuning and the red is the new tuning. You can see that it's nicely damped, and it gives a really good disturbance rejection response as well. And the variables you can see are quite different, the ones that were initial and the final variables. And that's the other thing about using technology to do the tuning, is that you can have confidence in the tuning that's generated, and you can input it almost directly without making any changes. It can be a little bit scary for operators, in which case you would put it in sort of a step at a time, but the end parameters really need to go in the way they are in order for you to really reap the benefits of the optimal tuning. And what we have here is the benefits here in terms of dollar values, really very significant, because you can imagine on a expander, on a gas plant where you want to maximize the feed, if you're able to have very tight tuning, then you can push these set points really close to the constraints that are on the plant. And here it's hard to see with the naked eye sort of what the difference is, but certainly in the blue one, which is the expander pressure PV, and the green is the set point of the expander pressure, you can see that there's an improvement in the variability, and even a small improvement ends up in huge amounts of benefits for these sorts of facilities. Okay, a couple more examples, and we'll get into some other tips and tricks, etc. Feed balancing. This is an interesting one. I think you would all have this sort of a problem on your facilities. You've got multiple flows or flow valves on a single, I would say, pipe, and it's a distribution, in this case, of sour gas from a sour gas header to acid gas removal units. So you have 3 acid gas removal units. There's 3 parallel flows, and this is an interactive 3x3 system. So you can imagine if they're all in manual, these valves, you open one of these valves, the flow through this pipe will increase, and these two will reduce, as you can see in this model here. So you open the valve and the flow in its own stream will increase, but the other two will reduce, and you can see that reflected in the diagonal. The off diagonals are reducing. So again, highly interactive. You could tune this manually, and a lot of people would, but you would never get it right, because if there were small changes here and there, you would find that it stopped working properly, and then you have to retune it. This way we understand the basics and then build the tuning on top of that using the technology. This is a little screenshot of our AptiTune technology where you can see how these loops are tuned. There's some default parameters that go in. You can choose, for example, the type of DCS you have, the type of equation you have, so it's very flexible. And you can also input the ranges. So in this case, the flow range of these acid flow valves is 0 to 620 kilonormal cubic meters per hour, and the output range is, of course, 0 to 100. And you can also enter initial tuning parameters that were there. In this case, there weren't any, so we just put some basic numbers there, and then it will calculate the final values for you. And this is a simulation of the result. Again, you can see how the behavior looks like with a set point change. The red is the PID, the process variable, and the blue is the valve output response. Now, this is an interesting one. This is about how to look at the stability of that PID loop. We have something we have defined which is called gain margin and dead time margin. It is a way of expressing how much change we can expect in that particular model, and how robust the PID tuning can be. So if we have some basic default parameters for gain margin and dead time margin. However, if you increase that gain margin and dead time margin, it will mean that you are creating a more stable tuning that is valid for a bigger operating range of that particular part of the plant. So in this case, if you are in a region to the right of this curve, it means you are basically unstable. So if you increase the gain of that model by a factor of 5 and you increase the dead time margin by a factor of 2, you're in this region here, which means that the loop will be unstable. So you want to make sure you are within this range here. And what the design we've got in this particular case is a gain margin of 3 and a dead time margin of 1. So if you stay within that area, it will work. So in practical terms, what this means is that the model can change. For example, if it was a heat exchanger that's fouling, you know that it's going to foul in 12 months time. Over time there's a certain amount of fouling. You can actually factor that into the tuning so that you have stable tuning throughout the life of that exchanger until it's cleaned again, and then it's back up and running again. And this is a before and after. I think the important thing here for this flow controllers is the fact that you are able to put them in automatic, and the operator can actually control the set point and set a desired value for those flows. There's no before and after, because this is one of those examples where they never actually put it in automatic because they were not able to. This one is my next example is again a very different kind of example. This is a gas distribution network, and really they take gas from several different facilities and they distribute it to power plants, and their sole sort of reason for existence is to make sure there is a continuous flow of gas available to these power plants, because these power plants then generate electricity for a very large city, and if there's problems in the gas distribution, then the lights go out. So it's fairly critical. And what we found with this client, they came to us and they have multiple sets of valves and multiple services for these different loops. So each sort of PID loop could be configured as a pressure controller and a flow controller. So we were able to set those up and tune them correctly so that they could operate this whole system or this whole network of pipes and valves efficiently and effectively. And you will see here, this is their some of their screens where they've got all these different loops, and on the right hand side you can see some of the tuning parameters that have been put in. What we did here was we improved the pressure control of this header at 410 psi, which was the operating pressure. So we pushed close to that and maintained it. We reduced valve chattering. All the PID loops have been set in auto for over 24 months now, and they were always in manual previously. There's more line pack. They can maintain the supply for longer periods of time in terms of the pressure. So you can imagine if some of the incoming gas drops off for some reason, there's a problem with the supply side, then because of the line pack they can maintain the supply for a longer period of time, which means the lights don't go out. And an improvement in the pipeline life. This is something the customer reported as well. So really, in this example, you could allocate a lot of benefit in dollars, but I think this is very much to do with criticality of an infrastructure that has been improved significantly. The operability has been improved significantly because of really improving the base layer PID tuning. We used our Inca Aptitune PID tuning tool for this, and the valves, like I mentioned before, were tuned for pressure and flow control. So we did that for both of them. So let's shift a little bit and talk about tuning itself. I think a lot of you, as was suggested by the polls, look at doing sort of tuning yourselves. And there is the quick tune option. So we make a set point change and we observe the response, and then we tweak the proportional action or the integral action. Typically we don't use derivative action. If it's slow, we observe it with visually, and we might increase the proportional action, in which case it might become a bit too oscillatory, and then we might reduce the proportional action. If we have a bias, an offset, then we know the integral action is not enough, and we might increase the integral action, in which case, it starts cycling, in which case we would tweak it a little bit more until we end up at a response which is reasonable. And in general, we don't use derivative action, but sometimes we do. So this is the typical, very simplistic way of tuning, and we are all doing this using either a visual method, or we will collect some data, we will put it into a spreadsheet using some kind of a spreadsheet method. There's lots of them available. There's also DCS vendors that have their own sort of methods, and so this is the typical way in terms of quick tuning. Now, if you look at model-based tuning, which is what some of the examples I showed you with those interactive models, What we want to do is identify bad acting PID loops from historical data or operator information, or you might even have a PID monitoring software that gives you this information. We want to be able to understand the process and the interactions available. We want to collect the data at a 10-second frequency, for example. And then if you have a 2x2 system, or let's take the example of the 3x3 system where you have those 3 flow loops that were never put in automatic, they were in manual, you would make steps in those valve outputs one by one, collect the data, then we would build the model and then calculate the optimal tuning. So this sounds cumbersome, but actually it doesn't take a lot of time. The first time you might need to set things up in terms of data collection. Perhaps you want to just, if you have the ability to collect data in Excel, that is good enough. In our case, the Inca Aptitude tool can import that data straight from Excel into the technology, and then we can do everything in there up to the point where you get the optimal parameters. So that is a different way of doing tuning, and I would suggest that that is the more rigorous approach, and that is really the way to certainly tune the more difficult problems. So let's look at some tips and tricks. So let's start off. As you know, a PID loop really is looking at the process side. So there's the measurement. So we must make sure that we understand that the measurement is working correctly. You will have noisy measurements, for example, in flows, levels. You could have analyzers that are frozen and spiky, and you might have instruments that are out of service. You might have calibration that's going on. So we need to understand that the measurement is working correctly when we are looking at these PID loops or tuning them or fixing them. And quite often, these measurements are not a problem, but sometimes you will need to investigate them further and you need to do something about them. So if you are looking at measurements that are noisy, then you want to be able to filter them. And if you want to filter them, then what you want to do is put the controller in manual. You want to trend the measurement by looking at some scaling, and then superimpose the raw and the filtered signal on the same trends to understand if the filtering is appropriate. So, maybe there's a noisy measurement, and then maybe there's too much filtering in this case, and then this one is perhaps appropriate. And there's some typical values that you can use, and I must stress these are not magic numbers. These are typical values based on experience. If you do need to filter, then filter the flows, not more than 0.3 minutes pressures, not more than 0.1 minutes levels, etc. But as always, you need to do your due diligence. You need to check yourself what service the measurement is in and whether it's very noisy, and it could be that the position of the sensor is incorrect, and which is also something that you might want to look at as part of improving the whole system. Now we look at valves. As we know, valves can be problematic. You have different types of valves, and you have the stiction problems, you have oversized and undersized, you have non-linearities. You could have control ranges not good enough. You could have missing positioners. So these are all problems that you'll come across. And the point here about valves is that, again, a valve is a part of the PID loop. So, measurement, valve, and all the other things need to be looked at when you are trying to fix a PID loop. So typically, these are not areas you would get into because you would assume that a lot of the time these things are working correctly, but don't overlook them. I guess that's the point here. And try and get to the bottom of it by checking these typical problems. Okay, so what is the what can we learn from PID tuning, or certainly what have I learned over the several years of my experience doing this kind of thing. It's important to take a systematic approach. So I would say start with your tuning exercise from the front of the plant to the back end of the plant. You need to collate the information, look at data from the process and look at the discussions, talk to people about, historically what's happened in certain parts of the plant. Maybe things are not working well and that's why they put the loops in manual. And, as an engineer, you need to collate all that information and come up with a understanding and then tackle the problem. These days, there are several tools available that can actually collect the information for you in terms of the PID loop performance, and they can present that information to you. But it's important to stress these PID loop performance softwares are not magic. They don't fix the problem for you. They just tell you where the problem is. And you still need to go out there and fix things. It's not a push a button and everything is going to work fine. The other thing I would say is do not be tempted to tune interactive loops quickly. There's always a temptation to tweak the numbers a little bit up and down and see what happens. But what you will find is you will spend probably more time doing that than using a systematic approach, because by using a systematic approach, you can be assured that you'll be done in 2 to 3 hours from when you started. With a trial and error approach, you could still be tweaking things in 2 to 3 days. So, like I said, it might seem a more cumbersome or a heavy approach to do the test and then collect data and input the data into the software and do the tuning, but in reality, it is actually much faster. And I would say always use a model-based approach to tune interacting loops. Building sufficient robustness in tuning is extremely important, and check for plant changes. So again, if you, example of the heat exchanger fouling, if you know these things are going to happen, then you can change some of the default parameters to something more robust that will allow you to do to develop a tuning that is much more robust over different operating ranges. Use historians without compression. Goes without saying, you have to make sure you understand the dynamics of the data, and if the data is compressed, then you won't get the dynamic information of that particular service of that PID loop. And I think this last couple of points are extremely important. I think there is a lack of, I would say, awareness at higher management levels, or even, at a technical level in some cases, on the benefits of what this does for us. And so, do before and after results, show them to your management, calculate benefits, if you are able to. Sometimes it's easy to do that on, say, energy saving type applications, and really create a little case study, a one-page thing that shows the benefits of these things, so you can, your management can allocate resources and to do this kind of thing on a regular basis. And I would recommend, although the title of this presentation is really about interactive loops, but I would say use a model-based approach for tuning all PID loops, including single PID loops, especially the ones that are tricky, such as temperature cascades or levels and things like that. So in conclusion, I would say there is a lot of benefit available by a rigorous approach to PID tuning, and you've just seen a few of the case studies, but there's several more available, and I'm sure you have examples of your own that you can try this on, and really use appropriate technology to tune interacting PID loops. Don't be tempted to do a quick tuning the way you have been used to. Try out a different approach, see the benefits, spread the benefit, the message across your organization so people are a little bit more aware, and then shine a light on this. And obviously a stable, well-tuned PID layer is really essential for a safe and optimal plant operation. So this is really something that everybody wants. We talk a lot about safety, we talk a lot about optimization, but not in the same sentence as PID. And I think we need to start doing that. I'm going to talk one slide about a little bit about IPCOS software and services. So we have a opportunity to offer you a free trial license. You can contact us through some of these emails that you see down there on this slide. So info@ipcos.com, or my email, which is sam.dhaliwal@ipcos.com. We've also got a web page that we've dedicated where you can go and look at case studies and papers and other sorts of information that's available to you. The other thing we can do, because we are fairly passionate about this whole subject, is if you send us your data and you've got some difficult, challenging problems that you want us to look at, we'll be happy to look at that and tune those PID loops for you, or interact with you and tune them for you, and you can go ahead and try out the new tuning that is generated using our technology. The other thing we're doing in this area is we're doing cloud-based PID tuning. So this is going to come fairly soon. There will be an announcement about this, where you do not need to purchase a Inca Aptitune license in the traditional way of purchasing, say, a perpetual license or an annual term license. You can sort of use it in the cloud on a pay-per-use type basis, and you will be seeing that coming up very soon. And lastly, next webinar, that's going to happen sometime in September, again jointly with IchemE, and you will see the topics probably being announced at least sort of 6 to 8 weeks prior to that. And we look forward to having you join us again for the next one. And thank you very much for your time. I really appreciate it. And we will just open it up to questions.
Thanks, Sam. Thanks for doing the IPCOS-sponsored webinar there. So we have quite a few questions in. So the first one is from Chris McNeely. He says, for the compressor example, what was IPCOS able to do that allowed it to be an automatic compared to what the controllers had with the commission design?
What we did was effectively, it was I think it was a GE compressor, if I'm not wrong. What happened was they never actually, whoever did the initial kind of commissioning of the compressor, they never really put it in automatic or tried it, and they never really put some decent tuning parameters in it. So whatever tuning parameters were in there, when they tried to put it in automatic, it immediately would go unstable. And because this is kind of like the heart of the system, it would create a problem for them and shut down the plant. So to be safe, they just left it in manual. So what we did essentially is we used our tuning methodology. We made some moves in the speed of the compressor. We got the variable output results. We then had to go into this is not a standard tuning algorithm, so to speak, because it's inside the GE software. So we had to actually get permission from them. And the client actually, we calculated the tuning, but the client actually had to put it in. So this was a very non-traditional type of tuning. This is not something we would touch normally, but in this case, because it was really causing them a lot of problems, they agreed, and we did the tuning using our standard methodology, and they just put in the tuning parameters.
Thanks, Sam. Chris has another question. This may be one that you'll want to discuss with him offline. He asked, what is the cost of the tuning process, and is there a cutoff point where it might not be financially beneficial for smaller sites?
No, I think I would say the Yeah, I think the cost we can discuss, offline as you suggested, Zaid. I think what tends to happen is, we would provide the software and the training for yourself and your colleagues. You would go on a training course, and then, once you're trained on the way to do this tuning or use this approach, you can just do it yourself. I mean, that's what we want to do, is to train as many people as possible in the use of our technology and also our methodology, I would say, so you can go ahead and use it yourself. So I would say the long-term cost is rather minimal in terms of our involvement. It would really be yourself and your colleagues who would do that. Obviously, if you need help from us, we would happily come along.
Okay, next question from Keith Jones. When you filter measurements, do you use the filter in the transmitter or in the DCS?
I think that really depends on your equipment. I would say, and also your philosophy, I guess, and how you manage these things on your particular plant. But I would say most of what I've seen is DCS filtering, because it's a little bit more obvious, and it's also easier to change, it's easier to manage. So that's probably where I would say is the easier place to do that kind of thing. I wouldn't think that it's there's no simple answer, but I would say typically I've seen it in the DCS.
Thanks, Sam. Keith had another question and a comment. He says performance of flow controllers is dependent on valve response, e.g. deadband, hysteresis, stroking times, and then he makes a premise: model-based tuning is less effective for these loops. Your opinion? Question mark.
That's a good point, actually, and I think although you would think that that is the case, because model-based tuning is looking at the actual performance of that particular valve. So if there is hysteresis and there is deadbands, etc., you might be able to catch that in the data. I know hysteresis is a difficult one, because maybe if you do the test between 30 and 40%, you might get a different response than if you did from 40 to 50%. So I can sympathize with that comment, that is not, the model might not capture all the different issues. And that's why I think that's one of the things you would discover if you are doing a test and you find there's hysteresis and issues, that maybe there isn't a way of implementing an optimal tuning unless you actually fix the valve itself. So, it's perhaps a process of discovery, that you will find that these issues have now, you actually find these problems, and then you can fix them from an instrumentation point of view. So I would say model-based approach might not work if you have those sorts of issues, but then I would say no approach would work, because if you've got fundamental instrument issues, then it doesn't matter what you do, how you tune it, it's just not going to work. The only advantage of using a model-based approach is that you can actually see from the data the problem itself, and then you can act on it and fix the valve.
Okay, next question is from Hakkun Yao. Can the tuning be done without the software, e.g. with Excel? We've actually got quite a few questions, so we'll need to rattle through them a bit now.
Yeah, I think the tuning, like I said, you can tune using just Excel programs. There are lots, you just Google it and you'll find several different people offering different ways of tuning using sort of Ziegler and Nichols approach or whatever else, and these are all sort of documented and in textbooks. But the point is that if you're doing a multiple interacting type tuning, then you will not find, you can't do that. There isn't any spreadsheet available that I know of that does that. most spreadsheets only deal with single loop tuning. They don't deal with multiple loop tuning.
Okay, and then Rob Hugoworth has asked, what is the maximum size of the interacting problem the software can handle?
We have not actually come across a major problem. The biggest one I have done is a heater with 8 passes. So you have 8, and then you have a temperature control that's 9, and then you have the fuel gas, which is actually a cascade. And so a 10 by 10 is no problem, but most of your problems will fall to within sort of, I would say, less than 5 by 5, and there's no problem with solving those.
Okay, and then Andrini Rissman has asked, what are the steps if tuning using a tuning software for the multiple pass flow controllers?
Yes, so that would be, the steps would be fairly similar. So you would put those pass flows and the temperature controller in manual, okay, and then you would make some step changes in each of those flows one by one, and you would make some step changes, let's say in the fuel gas, if it's a fuel gas cascaded onto the temperature. And then you would collect the data, you would build a model. That modeling is done in our technology itself. And once you have that model, you saw a couple of those matrices in my presentation, then you would use that to build the tuning directly. So that whole process is sort of seamless in the software. So once you import the data, you just go through all the steps and then you end up with the tuning.
Okay, still quite a few questions, so we'll have to get super quick now. I've got to say 3 minutes left. How do you decide for an interacting system what the best solution is, MPC or PID? That's from Rob as well.
Well, an interacting system, I guess the multivariable control is really about building on top of the PID layer. So you should always do the PID tuning of the interacting system first, and then if you believe that there is further benefits to be had to build MPC, then you would build that on top of the PID loops.
How is near collinearity handled or analyzed by the tool?
There is an inbuilt tool that deals with that. To be honest, because we're dealing with rather small problems, we don't have that problem in our PID tuning environment. Normally you would have collinearity issues in a APC or a multivariable controller where you've got lots of, a very dense matrix, for example, with lots of MVs and lots of CVs. But in our case, we're dealing with typically, like I said, less than 5 by 5. You don't see that problem.
Okay, and then Alvin Saldana has asked, can an initial model-based analysis of interacting PID loops be done using the dynamic tools in, e.g., AspenTech's HYSYS software?
I guess you could possibly do that, but again, it would be very much a theoretical thing. I think typically what you want to do is to really test this, to look at this, look at the PID loops in their actual environment, which you will find is very different from a simulation environment, because you will have things like hysteresis, like one of the attendees raised that issue. You'll have valve problems, you'll have measurement issues, and you want to be dealing with all of those in the real scenario rather than theoretically. So I would say it's best to do that analysis in reality rather than in a simulation environment.
I suppose there might be an argument on a brand new plant while you're still building it to try and be ready, but up for debate, I'm sure.
That's possible, yes.
Chris Openshaw's got a challenging question here. So he mentions software potentially being no substitute for experience. does PID tuning software potentially offer a false sense of security to control and instrument engineers who would not attempt this ordinarily? And then he points out that loop tuning on a live plant could be a risky process, causing upsets as a function of limits exploration. And then he mentions appropriate measures should be in place to mitigate and having competent people being involved in the tune. And he's being devil's advocate, of course.
No, I think that is a very good question. Like all different aspects of engineering, I think we have to be mindful of what we are doing on live plants. It's not just push a button and hope for the best. I think that's why I said even in our analysis of the model-based tuning or the methodology, it's a lot to do with understanding what you're dealing with. Understanding where the interactions are coming from, understanding the history potentially, talking to people. I had a bullet point there, collate the data and the information which is coming from the plant, and which basically means talk to people as well. And so yes, use the tool not just as a tool with garbage in, garbage out, so to speak, but really understand the data you're using and understand the results as well. Do some simulations before you enter the values.
Okay, last question. Are there any differences between your product and PID tuners within the DCS?
Yes, the main difference being that we are able to tune multivariable, deal with multiple interacting PID loops, while most DCS providers don't have that functionality available. I would say there's probably no other technology that offers this kind of thing. Certainly we were the first ones to offer tuning of multiple PID loops, multiple interacting PID loops.
Brilliant. Well, thank you so much, Sam, for a very interesting presentation. So we're out of time now, so we're going to wrap up. There will be a survey, please, to fill in as we end. So thank you, Sam.
Thank you very much for joining, everybody, and appreciate your time.
Brilliant. We will end now. So goodbye, everybody. And don't forget the survey. Thank you.